The installation is in violation of National Electrical Code (NEC) requirements. Firstly, consider the grounding electrode conductor (GEC). The GEC, or grounding conductor, must be connected to the transformer's X0 terminal and to the neutral bus in the panel. However, in this case, the GEC is connected to both the neutral bus and the grounding bus, which is not permitted. Secondly, examine the bonding of neutral and grounding buses. The neutral and grounding buses must be bonded together at the service entrance. In this case, they are not bonded. Thirdly, regard multiple electrodes. 2 electrodes are connected to the neutral bus, which is not allowed. Only 1 electrode can be connected to the neutral bus. Fourthly, focus on building grounding. The metal building must be bonded to the grounding bus, not to the neutral bus. Now let's delve into the specific NEC requirements. NEC 250.30 A1 states that the GEC must be connected to the X0 terminal of the transformer. NEC 250.32 B1 and C dictate that the neutral bus and grounding bus must be bonded together at the service entrance. NEC 250.24 A2 specifies that only 1 electrode can be connected to the neutral bus. NEC 250.56 mandates that the metal building must be bonded to the grounding bus. To correct these violations, the following steps should be taken. 1. Remove the GEC connection from the grounding bus. 2. Bond the neutral bus and grounding bus together at the service entrance. 3. Remove the second electrode connected to the neutral bus. 4. Bond the metal building to the grounding bus. Understanding these principles is crucial for ensuring a safe and compliant electrical installation. Let's further examine the grounding and bonding requirements, breaking down each element for clarity. Starting with the grounding electrode conductor, the purpose of the GEC is to provide a low impedance path for fault current to return to the source, which in this case is the transformer. Connecting the GEC to both the neutral bus and the grounding bus creates a parallel path for neutral current, which can lead to circulating currents and potential safety hazards. This is why the NEC specifically prohibits this configuration. The grounding electrode conductor must originate at the X0 terminal of the transformer and be connected to the neutral bus in the first disconnecting means of a current device. This ensures that the fault current has a direct path back to the source, allowing the overcurrent device to trip and clear the fault. Next, consider the importance of bonding the neutral and grounding buses. Bonding these buses together at the service entrance establishes a common ground reference point. This is essential for minimizing voltage differences between the neutral and ground, which can cause equipment malfunction and electrical shock hazards. The bonding jumper, typically a wire or busbar, connects the neutral bus to the grounding bus, ensuring that they are at the same potential. This creates a low impedance path for fault current, facilitating the operation of overcurrent protective devices. The NEC requires that this bonding connection be made at the service entrance, which is the point where the electrical service enters the building. Now, let's address the issue of multiple electrodes connected to the neutral bus. The NEC generally allows only 1 grounding electrode to be connected to the neutral bus. This is to prevent circulating currents between different grounding electrodes, which can occur if they are at different potentials. Connecting multiple electrodes to the neutral bus can create a ground loop, which can introduce noise and interference into electrical systems. In some cases, additional grounding electrodes may be required, but these should be connected to the grounding bus, not the neutral bus. These additional electrodes serve to improve the overall grounding system and reduce ground impedance. Finally, let's discuss the proper grounding of the metal building. The metal building must be bonded to the grounding bus, not the neutral bus. This is to ensure that the building structure is at the same potential as the grounding system, minimizing the risk of electrical shock. Bonding the building to the grounding bus provides a low impedance path for fault current to flow back to the source, allowing the overcurrent device to trip and clear the fault. The NEC specifies that the bonding connection should be made using a grounding electrode conductor or a bonding jumper of appropriate size. It's crucial to understand the differences between grounding and bonding. Grounding is the connection of an electrical system to the earth, while bonding is the connection of conductive parts to create an electrically conductive path. Both grounding and bonding are essential for electrical safety, but they serve different purposes. Grounding provides a reference point for the electrical system, while bonding ensures that all conductive parts are at the same potential. In summary, the NEC violations identified in the initial installation include improper grounding electrode conductor connections, lack of bonding between neutral and grounding buses, multiple electrodes connected to the neutral bus, and improper grounding of the metal building. To correct these violations, the grounding electrode conductor connection must be removed from the grounding bus. The neutral and grounding buses must be bonded together at the service entrance. The second electrode connected to the neutral bus must be removed, and the metal building must be bonded to the grounding bus. Adhering to these guidelines will ensure a safe and compliant electrical installation, protecting both people and equipment from electrical hazards. Furthermore, understanding the relevant NEC sections is crucial for ensuring compliance. NEC 250.30 A1 provides specific requirements for grounding separately derived systems, such as transformers. It clarifies that the grounding electrode conductor must be connected to the X0 terminal of the transformer, which is the neutral point of the secondary winding. This connection provides a direct path for fault current to return to the source, allowing overcurrent protective devices to operate effectively. NEC 250.32 B1 and C address the bonding requirements for separately derived systems. These sections stipulate that the neutral bus and grounding bus must be bonded together at the service entrance. This bonding connection establishes a common ground reference point, minimizing voltage differences between the neutral and ground. The bonding jumper must be sized appropriately based on the size of the ungrounded conductors, as specified in NEC Table 250.102. C1. NEC 250.24. A2 limits the number of grounding electrodes connected to the neutral bus. This section states that only one grounding electrode can be connected to the neutral bus. This is to prevent circulating currents between different grounding electrodes, which can occur if they are at different potentials. If additional grounding electrodes are required, they should be connected to the grounding bus. NEC 250.56 outlines the requirements for grounding metal building structures. This section mandates that the metal building must be bonded to the grounding bus. This bonding connection ensures that the building structure is at the same potential as the grounding system, minimizing the risk of electrical shock. The bonding connection can be made using a grounding electrode conductor or a bonding jumper of appropriate size. It's also important to consider the size of the grounding electrode conductor. The size of the GEC is determined by NEC Table 250.66, which is based on the size of the ungrounded conductors. The GEC must be large enough to safely carry the fault current back to the source. Additionally, the grounding electrode system should be properly installed and maintained. The grounding electrode should be driven deep enough into the earth to ensure good contact and low impedance. The grounding electrode system should also be inspected periodically to ensure that it is in good condition. In addition to the specific NEC requirements, it's also important to follow good engineering practices. This includes using high-quality materials, proper installation techniques, and regular maintenance. By following these guidelines, you can ensure a safe and reliable electrical system. Let's also discuss common misconceptions about grounding and bonding. One common misconception is that grounding is only necessary for safety. While grounding is essential for safety, it also plays a crucial role in the proper operation of electrical equipment. Grounding provides a reference point for the electrical system, which is necessary for accurate voltage and current measurements. Another common misconception is that bonding is only necessary for metal parts. Bonding is also necessary for non-metallic parts that can become conductive due to moisture or contamination. Bonding ensures that all conductive parts are at the same potential, minimizing the risk of electrical shock. It is crucial to remember that these NEC requirements are in place to protect people and property from electrical hazards. Ignoring these requirements can lead to serious consequences, including electrical shock, fire, and equipment damage. By following the NEC and good engineering practices, you can create a safe and reliable electrical system. Furthermore, it is important to understand the concept of impedance in grounding systems. Impedance is the opposition to the flow of alternating current and is measured in ohms. A low impedance grounding system is essential for providing a quick and effective path for fault current to return to the source. High impedance grounding systems can limit fault current, which can delay the operation of overcurrent protective devices and increase the risk of electrical shock. The impedance of the grounding system is affected by several factors, including the size and length of the grounding conductors, the type of grounding electrodes, and the soil conditions. It is important to carefully consider these factors when designing and installing a grounding system. In addition to the NEC requirements, there may be local codes and regulations that also apply. It is important to check with your local electrical inspector to ensure that your installation is in compliance with all applicable codes. Moreover, it is also crucial to maintain proper documentation of your grounding and bonding system. This documentation should include drawings, specifications, and test results. This documentation can be helpful for troubleshooting problems and for future modifications to the electrical system. Remember that electrical safety is everyone's responsibility. By following the NEC, good engineering practices, and maintaining proper documentation, you can help create a safe and reliable electrical system for yourself and others. And finally, always consult with a qualified electrician if you have any questions or concerns about grounding and bonding. A qualified electrician has the knowledge and experience to ensure that your electrical system is installed correctly and safely. By understanding these principles and following the NEC requirements, you can ensure a safe and compliant electrical installation related to transformer grounding and bonding, protecting both people and equipment from potential electrical hazards. Always remember that electrical work can be dangerous, and it's essential to prioritize safety in all aspects of electrical installations.